Yeah, so we're into week 3. So unit 2. We're getting through the algorithmic stuff. Chat bar's annoying. You can see it over the side. I hope that's not too irritating for the rest of you guys. Yeah, so we're into unit 2, we're getting towards the end of it actually. So yeah, just do a brief review of where we got up to last time, just so we're all on the same page, and we'll see where we're going. So analysis of algorithms. I know you're all doing this first homework thing, so you sort of, I think that the primes, the Goldbach primes, is a really good one for illustrating this analysis stuff, like where it's important. Yeah, so we introduced a very simple sorting algorithm, not one you use in practice, bubble sort. You can see it here. Hopefully you guys are starting to get familiar with this stuff, that you just eyeball this function and you can go, oh, okay, I've got 2 loops. It's doing all this complicated stuff in the middle. That seems like it's going to be n squared, just because it's like looping over the same thing twice. So you got to do it again and again and again. Think about the rate limiting steps. So, you know, doing this tests, accessing, swapping stuff around. So accessing elements in an array, swapping things around will be computational bottlenecks compared to just iterating through this array. So, you know, that's where it's doing all the work, and that's like that squares with the length of this array. So yeah, so we did a little bit of mucking around and profiling and show that, yeah, it looks quadratic. It probably is quadratic. Let's just count how many operations it does. Yes, it is quadratic. Hope everyone's okay with that. And then comparing it with inbuilt sort, we can see that inbuilt sort flogs it. Like it's like at 10,000 elements, it's over 100 times faster. So 2 orders of magnitude. And we can see that this is scaling like n log n. So this naive approach in bubble sort, where you sweep over the array, swap things around that are out of order, then sweep through it again and sweep through it again and sweep through it again, probably not the best strategy for sorting. You can do tricks, software engineering tricks to make it quicker. You can do inbounds. You can, no, maybe not for this problem, but other ones. You can stop type conversion, type instability problems. It's still not going to make you win that much. If you're scaling like squared versus n log n, it's never going to win unless the coefficient out the front's really bad. Okay, that's where we got to. Then we started on arrays. Whirlwind type of data structures. We looked at how arrays are laid out in memory in Julia by looking at this pointer to the data. So that's like an address in memory of where the data is for the element in the array. And you couldn't see for this multi-dimensional arrays, you can see when the data type's the right type, when we've got int 8s, so they're really nice and small, 1 byte apart. You can see that going down the columns, then across the rows, as that iterates through, they're only going up by 1. So they're closer in memory as you go down in columns. It's column major set up for arrays in Julia. Now, I got angry at this. So the astute amongst you will notice that this is different from last week, because after I went through it last time, I got angry at it and I went, that's stupid. It's not showing what we were supposed to show. So I rejigged this. So to do the timing better than it was being done before. So we've got 2 functions, one where we sum up over the rows of the data. So what that means is we're going through the array, let's find an array, through the array this way. So 1, 4, 7, 10, 13. So this spacing is further apart in memory. So you'd expect something called a cache miss if you're iterating through that way. So it should be slower. Whereas if you go through the columns, so the tight one, when you're indexing this array, the fast one is happening going down. That one should be faster. So we've made a very non-square array. So it's 500 down, 1,000,000 across. Randomly generate this one. One of the tricks, this is for timing for you guys, if you're ever trying to profile stuff, a good idea is to run it once before you time it if you start a REPL session, because it'll help with pre-compilation. So just one run through and then actually time it. So previously we were timing these things separately. So if we time over the columns, 0.6 of a second for this guy, if we sum over the rows, we got 6 times. So it's 10 times slower going across than it is going down. So the whole idea is that for you guys, I guess, big point for this is that even though access of these elements is supposed to be order 1, it's not actually true. And another lesson after me going through this and changing it and fixing up the timing is that be careful with timing because it's hard to sometimes these timing macros won't be the most reliable. Again, I've said this before, but you probably want to use something called @btime from benchmark tools. So if you're in Julia, I hope this is big enough. Oh, let's make it a little bigger. Because my computer's dead, but using benchmark tools is the one. You can add that package. I use that when you're trying to be serious about timing. You want to do something a little bit. It'll do a statistical sample and it'll do this dry run for you, and you don't have to worry about it so much. But we're just being rough. It's quicker to run. So just you can verify this one yourself, hopefully on all of your different computers, because all computers are different. The same array access pattern is, the same thing should happen, but we'll see. So please let me know if you run yourself and you get something different. Well, it'd be interesting to examine. So that's one of your basic data structures. So what we're going through is different data structures. So we're going sideways through data structures to give you an idea about how a way to speed up this sort problem. Multi-dimensional arrays. You guys happy with working with those multi-dimensional arrays in Julia? I'll probably just say a few little things just for syntax stuff, in case this is confusing you. So making a matrix, let's not go zeros, let's be more interesting, go rand. So some random numbers. When you do this, it's called a slice. Has everyone seen, you've probably seen this and been using it probably in your homework. What this does is it will make a copy of that one. So if we swap it around, we got that one. So one of the things you'll notice if we look at type of X is a matrix, which is just an alias for this 2-dimensional array. If we look at type of the slice, it's a vector. So it's an array of float 64. The same if you do this one. So I know in some other numerical libraries, when you do this, what you don't actually get out an array, you'll get out a matrix that's like 1 by n or n by 1. And doing multiplication makes more sense. Whereas some of you guys have probably seen this. If you go straight away and try and do something like x1 colon times this. Oh. Sorry, my hand slipped on the keys. You might be expecting something, I call it X. There it goes, there's no method matching multiply for a vector and a vector. You got to worry about the shape of these things. So if you want an outer product, you want an inner product, inconsistent dimensions that way. You can also, if you're using linear algebra, you can do dot product. Is a thing you can do. You'll have things you can do, because it's sort of, if you think about it, just arrays, you sort of got to tell it how to work, or it won't make sense. Yeah, so for this one, we'd need to do that way. Then we get a single number. So that's an inner product. That guy's an outer product. And you get all these overloads, multiple dispatch. So you could go like, say C equals zeros, 3, 5, and you can go C plus equals that guy. Sorry, I can't drive my mouse today, I'm having problems. Yeah, plus equals, plus equals, plus equals, plus equals to update C. So, be careful of the shapes of these things, be careful when you're slicing what it does. For performance, when you're doing a slice, you're actually doing a copy. So that's not always what you want to do. Sometimes doing just an iterator at a lower level is going to be faster. There's something called a view, but I won't confuse you with that if you just want to look at what's in there. Any questions on that stuff so far? Just thought it would be a useful sideways thing for you guys. All right, deafening silence. I'm going to take, oh. Okay, I got a question in the chat. I'll address that one in the break. I think that's a good way to do that. That's fine. Okay. Yeah, no more questions. I'll keep going on. Cool. So next data structure that's going to be useful for you guys is a thing called a dictionary. These are super useful, and yeah, you use these all the time. It's like, I guess it's premature talking to you guys about this stuff, but later on, you're going to be building your own types in Julia. Till you get to that point, you know, where you've got your design of your program's not quite right. This really useful thing is a dictionary, and you can have nested dictionaries. The whole idea of a dictionary is it's a collection that has keys that map to values, and this can allow for efficient lookup. This is like, yeah. So the thing is, I guess, what's the big point? So that's your idea if you're going to use it. So you can imagine straight away that's really useful. For constructing dictionaries, it's pretty simple. You just use this x equals dict, and you can give it types. So typically this guy will be a string, and this guy is whatever you're going to be working with. So, you know, sometimes it'll be an array of int 1, and then that will initialize an empty dictionary. And if you want to add something to the dictionary, you can go x 1 equals 1, x 2 equals 1, 2. And then you've got this thing with keys mapping to values. So I'm putting an array in that. This is the key, this guy, and this is the values. And if you want the keys, you can get keys of x. If you want the values, you can get the values. You can iterate through these things. So for k, v, x, at show k, at show v. You can iterate through keys, values, do stuff. So straight away, I hope you can see that this is a super useful data structure, especially that the key lookup is really fast. We'll go through a little bit of example about this, but just to, that's the real killer for this stuff when you're worrying about performances. You want this key lookup to be really quick. And it's very clever how it works inside in Julia. There's an example here of like postcodes. So, you know, so you can go, so St. Lucia has postcode 4064, South Brisbane has 4101, I can't read, Rochdale 1302. So accessing by the keys, I just showed you that before. You can do this guy, it'll complain because we haven't put a key to Ringa. Another one that's not in the notes, but it's really useful is get. So you can go get to Ringa, and you can go give the thing difference between get and that access thing is if the key is not in there, what do I do? And you can go not found. So get to Ringa. Yeah. Whereas if you get one of the keys, South Brisbane. Yeah, it doesn't have to be one-to-one mapping. Like I showed before, like this example here, you've got, you know, one key going to one value, but you can have arrays, you can have dictionaries of dictionaries of dictionaries, you know, all the way down. You can have very, very complicated nested structures with these things, and it can be really useful for storing data. So yeah, so I got a question from Natalie. Although don't dictionaries use more memory than some other data structures? Yeah, that's true. access will be slower than, if you have a perfect lookup like an array, like if you can go, I know this index is 1 and I have an array of values, you've got a way of calculating it. That will be faster than a dictionary as well. But it's just a, pragmatic things decide why you use them. They're just so useful that you just use them all the time. Typically, I'd say for this one, you're thinking about sorting and searching. The really useful one is if you can map data to a key. So then you go, oh, I've just got this bit of data. So let me think about this one as an example. So, or, you can have multiple suburbs with a postcode. So sometimes the reverse dictionary is more useful, where you're going to go, I'm going to get all the things in here and then find the one I'm actually interested in. So the way I use dictionaries for acceleration and searching for things is nearly always this way of like, there's all these things in this big array. I don't want to scan through all the array. I want to do an expensive test on a subset of the array. So if I can map those things to a key, then use the key to get those things and then do the expensive tests. That's really, really useful way to make things faster, because then instead of having to search the whole array for all the things or do the expensive test on all the things, you can do this fast thing, get the little bits, you're interested in, and then work with it. So I got the question. So what sort of stuff can we do for the default? Depends on your problem. Like usually what you would do is nothing, right? Like, Julia has a special thing. I've got to come up with a suburb that's not in go way north. So nothing. Nothing is a thing you can use in Julia. And you can do a test like is nothing. That's really useful. So you can go, I'm going to get this dictionary, and then there might be some test like is nothing, get true. So then don't do things. And you can just push new keys in the dictionary at any time. So for that second follow-up question, you can just go dict blah. As long as the types stay the same, you'll be all good. So somewhere in New South Wales, it's called blah apparently. But yeah, you can keep, can't have the same key twice though. So if you use the same key again, you'll override the thing that was in there. Yeah, that's it. You can do all these things like you can delete things out of the dictionary as well, but you guys can have a play and look at the docs and work that stuff out. So because we're talking about algorithmic stuff, it's good to think about how you might implement a dictionary yourself. And so there's an example here of just doing it as 2 arrays. So yeah, you can do it with just arrays. Maybe straight away you'll see what the problem with that is. So we've got an example here where an array of keys and an array of values. So this time this is string and this is int and undefined. So, I hope you guys are familiar with both. You've probably seen this 100 times now. Defines an empty array. You can also do this, which is much shorter. If you don't know the size and then start pushing stuff to it. Same thing, different ways. So there's 2 functions defined here, add key value pair. So doing the same thing, we're going to push through. And then value of keys. So this is pretty rubbish way of doing it. So we're going to go, so value of keys, key, value, key in question. So enumerate the keys. If the key is equal to the key in question, return the value of I. So it didn't find. So you could do this one as a get, though we were talking about before. I was saying there's this useful function get. You could do your own my get default. So you could use my get like that instead of the one that's there if you want to make it like the Julia base one. So now straight away you should be able to see when you're doing this enumerate. So I've mentioned this one before, super useful thing for when you're iterating over an array. You give you the value of the array and the index of the array. This is function enumerate. And we're doing a test of equality. So this is kind of rubbish because that's going to be straight away, it says down the bottom, but order n. So the length of the keys, you're going to go through them all, do this test one at a time. That's pretty rubbish way of doing it. So the typical way to do it is this thing called a hash table data structure. If you're really keen, you can go and have a look on this into these hash tables, how they work. Really useful, really important. And if you're really interested and you want to meet your lecturer for the third part of this course, this is Julia talk on this one. I won't click the link because it'll start talking, but that's Andy Ferris's talk on an alternative way to implement dictionaries to make a lot of things really fast, mapping, doing crazy things like maps over dictionaries. So for your edification, I've probably said this one lots of times, you can do a map over an array, but map over a dictionary, map's not defined over dictionaries. When sometimes, this is Julia, not a thing not supported in Julia. So something Andy's been working on as a side project is this alternative things where you can do crazy things like that, and it's fast and efficient. I recommend the talk. It's probably make your brain hurt a little bit, but that's okay. Cool. Basic introduction to dictionaries. I've used these a lot, use these all the time. Sometimes these custom ones, where the most useful one I've found is when I'm doing spatial acceleration. So if you can go from data to the key. So all these types of, all these things, like if you're trying to, I guess the prototypical example is something like doing nearest neighbor search. So you have a bunch of points and you want to find all the points within a circle around this point in some n-dimensional space. You don't necessarily want to, this is an n squared thing, that the list of points could be huge. You don't want to search through and go, is it inside the radius? Yes, no, blah. So one thing you can do is you can sort of chunk up space into volumes, and you can give the volume a key name. And if you can map from a point to the volume it lives in, so this is like a deterministic postcode, I have these coordinates, I go into this special named box in space, I can get all the points within that box just by calculating the key for that value. That's really useful spatial acceleration structure for doing those sorts of searches. That lets you go, from n squared to n log n for doing those sorts of searches. Any questions on dictionaries before I move on? No, cool. Another one that's useful, base data type that's supported in Julia is is sets. So these are like mathematical sets. So I shouldn't have to tell you guys about this, but a set, it's a bag of things with no repetition. So just like a set in set theory in mathematics. So they're unordered, no repeats. So if you look at this set, we're defining a set with an array of values. 1, 2, 3, 4, 1, 2, 3. So 1, 2, 3 are repeated elements in the set. So this special data structure set keeps track of repetitions and won't let it happen. So that's really useful. There's an example here. You can do all the usual set theory shenanigans you're interested in. So you can do intersection, union, set diff. You can do the complement with respect to stuff. So there's examples of this here. So I'll let you run through it yourself, but different ways of defining the sets. So you got A, 2. So again, with repetition, it's not going to be repeated. Yeah, there's a question there from CM. Does this mean that indexing into a set is not possible? It doesn't maintain order? Yes, that's right. So what you use a set, so what you would use a set for is you want to know if something's in something, but you don't really care about what it is. It'll be fast to tell whether something is inside a set. That's what you want it for, but you don't necessarily want to know what the particular thing is or do anything with that value. You just want to know It's a bag of stuff. Have I seen this thing in this bag of stuff before? It's optimized for that. Yeah, so the thing you would do is you'd go like s equals set 1 in s. True. That's the side of the test. You know, you want to do, if you want to do set theory, or you want to do intersections or unions, so t equals set 3, 4, 5, and yeah, just make sure the syntax. So, whoa, my mouse is playing up that time. So you can do intersect st. So the only thing in the intersection of those two sets, I'm not, that's a good question. So is the in operator in set is order 1? I don't think so. I think it does scale with the size of the set, but not badly. Good question. That's one to look up. It'll be like looking up something in a hash table for a dictionary. There'll be an optimized algorithm for saying whether this thing's in there or not. I don't think it would be constant time lookup. Someone wants to be really cool, they can go off and actually write a test for that and see the timings as you increase the size of the set. I'm not actually sure. I suspect not, but I suspect it's very fast. So faster than an array anyway. So doing it in a set versus in an array will be way faster. Yeah, you can do, so all these examples, union, intersection, so they're just called union, intersect, set diff. So, you know, in set theory, it might be B minus A. Set diff super useful, but it's you have to remember it's the side. So, you know, 2, 1 is in S, but not in T. 5, 4 is in T, but not in S. Yep, that's all of them pretty much. They're the usual set. You can do is subset, all these things, good fun. So there's a little example here of doing timing with these things of is an element of the array, is an element of the set. And you can see that, so I'm not sure we're setting up array data. Oh, there. So random set with 100,000 elements, and I think there's a question there. One of you guys can go off and work it out. Like if you have int32s, what's the probability of getting a repetition? Like how many times would you have to run this before you say had a 50% chance of seeing a repetition? So the set would be less length than what you initialized the array with. I'll leave that for you guys. It's simple, should be a simple probability thing. It's like a birthday paradox thing. Or birthday problem, I should say. int32s are big, so not much chance. So accessing it in the array. So I think that's the element. No. Oh, yeah, in. So that, I can't remember the locate. So that's just in. So that's that symbol. You can use that if you really like get excited by Unicode. You can do that, or you could do in. So the one I was doing for us, I was just writing in X in my set, or you can do this funny little element of, if you like it looking more like maths. Yeah, so check whether it's in the collection. And what you can see for this size array, and be careful with timing, might not be the best way to do this timing, but accessing in the array is like way, 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 way slower. So I can't even count how many zeros different that is. So 8 divided by this. So yeah, 2000. So 3 orders of magnitude. So you start, when you're doing computer stuff and you're worrying about performance, you start counting in orders of magnitude. So that's huge, 3 orders of magnitude. Again, use a set when you need a set. When the tests you want to do are set theory type operations. If you want an array, use an array. I guess that's the big takeaway. So the data structure should be tailored for your particular problem. Using the things willy-nilly, yeah, not great. So like, you don't want to be getting all the elements of the set and checking whether the thing is there when you want to index into it. If you actually want, order is important, make an array. Cool. Any questions about sets? No? I don't quite know how long to wait. It's useful. I actually use this one at work, so we use sets. Okay, so there are two really basic ones. Okay, we're getting to the important bit for you guys. So priority queues, heaps, and back to sorting. So let's try and think about how we're going to talk about this. So there's heaps and heaps of data structures that you might use in practice. There's lots and lots you'll end up learning about if you do this stuff. So things like, what would you use for a general database, like an SQL database? Like, what's the data structure for looking through data for that thing? And then compare that to a geospatial database where things are, in 3D space, and you do queries on things that are close together. Like, what sort of data structure would you use to make queries over that stuff fast? They're two very different things. So the problems are different. What a data structure is, the idea is that as I create this thing, it allows me to do the types of queries I'm going to do faster than I otherwise would be able to be. That's the whole point. So I waste a bit of time with creation and memory for these things, and then it allows me to do a query really fast. And if that's the thing I'm going to be doing all the time, that's when you'd use this data structure. So data structures and algorithms are like this. A canny data structure is basically the answer to most algorithmic problems. The other one I should say just before is like flipping things around. Only do things once if you can do things once. When you look at bubble sort and you're going, I'm sweeping through and sweeping through and sweeping through and sweeping through. Could I be doing more things at every step? So I'm not, wasting cycles doing things again and again. That's one sort of trick to algorithmic thinking. The other one's thinking about data structure. So is there a particular data structure I can use that would make my life easier for sorting? So there is one that's very important called a heap. So a heap's really confusing because it's overused in computing. That's talked about here. There's this thing called a heap, which refers to a place in memory where allocations happen. And there's a little bit about heaps used for allocations of immutable types and that's garbage collection, but they're going to talk about that in Unit 4. I won't confuse you with that stuff. So just as a bit of annoying overuse of terms, heap will be used in these two different contexts, and they mean two quite different things. So this guy is a data structure called a heap. I'm not gonna confuse you too much with what's going on with it. It's a special way of having data in an array with this tree-like form. You guys are going to go and implement this stuff later on. So you're going to use it again and again. So I'm just going to introduce it. If you're super keen, you can go off and read it and understand it and implement your own before you even get to it if you want to. Heap is useful because it lets you do something called a priority queue. So in my day job, priority queues are super important for simulations. So basically, when we do a simulation at my job, we're simulating things through time. We want to know the next thing to do. And you give these things a priority, and you want to know what's the next thing I should be doing. And I want to be able to get this thing from this data structure. And then if I get a new thing that I know I'm going to need to do later, I need to put it in that data structure, and it will come out at the right time. So this thing of like, how would you do a priority queue? So usually the things you're going to want to do is you're going to go, what do I do next? I have a new thing. I want to put it back in the queue, and I want to go to a thing in the queue and change its priority. So something's happened, it's changed the state of the world, and I don't want to this thing's not important anymore. I want it to go backwards in the queue. They're the 3 operations you want to do. So there's an example here of, I have to remember what this is. So it's lots of people turning up at a mass vaccination center. You know, queuing stuff, there's a million examples. Usually it's like going to the supermarket at the checkout is the usual example, and you've all got to line up and who comes next and what type of queue. So in this one, we're going to go, every individual's got a name, which is a string, and receives a priority for vaccination, which is a number, say float 32. So that might be based on a whole bunch of factors. So this individual's age, they have a, you know, if we're thinking about COVID, you know, are they immunocompromised? Are they a frontline worker? Blah, 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 blah. You know, all these different things, they might go to giving a particular priority. Yeah, age, occupation, medical condition. So there's lots of different priorities, and you want to go like whoever's in the queue, who's next. And you want to be able to do that quickly. So, yep. So when the priority is highest, they're called. So this is the thing. You want to be able to. So if people turn up at some arbitrary time, you want to be able to add them to the queue. You calculate the priority, put them in the queue. You want to look at the whoever's next. So you always want to know really quickly. So this data structure is all optimized around, I want to know who's next really, really fast. And the other 2 are lower down priorities where you want to be able to add people really quickly. You don't want that to be slow, but it's more that I want to pull stuff off really, really quickly. And I want to be able to modify stuff really quickly, reasonably quickly as well. Yeah, so this is usually called pop for this guy, and this one's called push, and this guy's, I can't remember what that guy's called, but they're the operations you do anyway. Names doesn't matter too much. You can do a priority queue in lots of different ways. A heap is a really, really efficient way of doing a priority queue, especially if it's lots of elements. So for mine, I'm saying like I'm doing all these simulations in a business, and there's thousands of them, and they're quite expensive, and I need to do them in the right order. So this must happen before this because causality gets broken. That's the kind of stuff we do. That's the setup. You can probably imagine that's a useful data structure. Think a little bit ahead about how you might use that for sorting. We're going to do a small little digression onto named tuples, which is a way to keep track of individuals. So this is another useful thing in Julia, a named tuple, which is a little bit like a dictionary. So before, you guys have seen, you know, tuples. You know, this, you know, you'd use this as a function signature, like that's a tuple. So sometimes it's really useful to have named tuples. No, it's not. That's a name. This thing's called a name tuple. So type of this thing, it's a name tuple with 2 names. So another bit of syntax you'll see in Julia is this little dot dot. That's defining a thing called a symbol. So if I go, let's see type of this guy. Oh. Tragic how much I can spell. So that's a symbol. That's really useful. You can think of this as like a string pretty much, but not quite. It's faster. So one of these interesting things about the implementation of Julia, we were talking about dictionaries before. If you have a dictionary where the keys are symbols, it will be faster to look through. That's not super important to know, but it's something you might be helpful for you one time in the future. I've had that problem in my day job, like needing to make dictionary access really fast. So doing that get from a dictionary, if you have the keys as strings versus keys as symbols, the symbols one will be a fair bit faster, surprisingly faster. So that's a name tuple. You've got this thing, so it's 2 things. It's got these 2 symbols. It's a tuple of names and a tuple of value types. Really convenient to work with. know about it, bit of syntax for your, I guess, collection of tools, your bag of tricks for when you go to do problems. Cool. Again, you can make this name tuple like a dictionary. You can make the collection really complicated. Oh, I should say, if you want to index, you can do name. And so I'm just pressing dot and tab, and you can get the fields. We'll see if it's field names. I think it is. No, it's not field names. That's for a type. Anyway, might come up later on. You can see it in the type signature anyway. What these things. So what we're going to do is going back to a priority queue, and again we're going to be naive, and we're going to see that being naive is not great for performance, and have a look at the algorithmic complexity of what we're doing. So we're just going to keep an array of name tuples. So what's the difference between a dictionary and a name tuple? You just can't edit the tuple, perhaps. Yeah, so it's more like, that's a good question. I'll probably get back to that one, Ethan. Just go on. So yeah, different things, you'd use them for different things. I'll try and come up with a good answer, I think is what I'm saying. So I'll put it off for a little bit so I give you a good answer. I'll think about it in the background. So here, again, this is the type of this name tuple, and you can initialize an array of name tuples. That's all that syntax is saying. So this is a bit of a mouthful, you know, going priority name, blah, 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 square brackets. So that's just an empty array of name tuples with priority and name. So we're going to just push because it's an array. So, you know, I was saying about you want to add a thing to the queue. That you probably, and usually you give that name push. So I'm going to add a thing to the priority queue. I'm going to call it push. I'm just using, you're going to use the array push. So, you know, that's fast. So that's good. It's easy to push things to an array. The only problem you've got is memory use, but you have that same problem with a heap as well. So like if you know performance trick in general, if you know the size of an array, initialize it with that size, don't allocate memory. Allocating memory is the slowest thing. Julia will do tricks to make it fast to allocate memory by, you know, preemptively allocating when you start doing this stuff. So that's not as bad as it could be, but just as a general thing, if you know how big something's going to be, fill a thing in with undefined of that size and then put the elements in as you go. If you don't know, you just have to push, and it's not too bad. So here's this priority queue. So I won't run the code. You can see there's a couple of priorities, and yeah, so they're talking here about the notes doc here about this thing I was saying about every time new memory needs to be allocated. It's clever underneath in how it does that. Most programming languages are, so that, you know, it's not going to be really bad. But removing is going to suck. So this is going to be order n. So you have to search through this array to work out where you're going to put it in. That's order n. That's not as good as it could be. So but you can sort of get this imagine that, you know, yeah, I won't talk too much about that. But so bit of syntax, you know, maybe this is something you delete out is what you can use for an array. You give it the array and an index and we'll get rid of them. So that's if you want to get, that's removing an individual is slow, order n, and searching for an individual is also going to be order n, which is, you know, just like this thing before, you're going to go through all these things, find the one with the max priority. That sucks. Yeah. Anyone got any ideas about what you could do with an array data structure that might make it faster for doing this? Like at least finding the top one. Yeah, you could use the built-in one max. What's something about the array itself? Could you do something when you're doing insertions and deletions? It might be a little bit more clever, I guess is my question. So something about the array itself. If you want to be, yeah, cool. Emma's one, store it sorted. So that's going to push the cost onto when you're inserting though. That's the problem. But if you only care about when you're pulling off, yeah, sure, sort it as you put it in. It's going to be fast to find where you put it in because it's already sorted, and be faster to find the spot because you can do a better job than just having to search through the array as in random order, order in at worst case. If it's sorted, you could do something. You could imagine doing something like a bisection search where you go, I'll look in the middle. Oh no, don't have to worry about that half. Blah blah blah. Make it log n. Little useful function for you guys is, we were talking about in before. If you have a sorted array, Julia has a built-in function for finding whether something's in it that's faster if you know it's sorted. It's got to be a sorted collection though. So if you have a array and you know it's sorted from the start, you can use in sorted and it will be faster than in. Might be useful for you guys. I don't know if you might not have seen that one. Yeah, so you can do a better job if you know the array is sorted, but then you're putting the problem onto, oh, I've got a new thing and I've got to put it in the array. I'm going to delete something. Deleting should be fine, it'll still be sorted, but insertion will be the problem. So, yeah. So order n's not great. So the heap data structure is a tree-based way of, so in computer science, you always talk about a tree where there's a root node, everything comes down, it's a graph, it's directed and acyclic and always going down. Smarter tree-based way to keep the elements of priority queue. So you're going to go through this in detail later. With this data structure, constant time lookup for finding the top priority. Deleting the maximums log n, which is cool, and insertions are log n too. And updating a priority is auto log n. So think about it as a black box. It's going to come back for you guys. You're going to know more about this than I do by the end of this course, hopefully. Have a think about. I'd totally suggest you read forward though and work out, implement your own heap data structure and then use the Julia one and see if it's better or not. This still come back. If you've got free time, it's always good to look these things up. One thing about coding is there's no shortcuts. You've got to code a lot, and doing these sort of things as an exercise is always a really good idea. So data structures is a very, very useful package in Julia. I should have it. Nope. I do use it. Has many, many useful data structures implemented in base Julia. You can see through all these things, all these different things, too much stuff. But one of them is a heap, and it will be useful. So, okay. So I'll just give it a break there because we've been going for 50 minutes. I will return. I'm going to look through this question. Someone asked me a question before. I'm going to go back to it. Does anyone have any questions before I stop there, though, on what we've just gone through? Okay, I'll let it go. Take a 10-minute break. If you've got any questions, feel free to put them in the chat. I'll go on to silence though, so I don't annoy people. We'll come back in 10 minutes or so. Thank you. Okay. So the question I got was about including a function as an argument. Okay. the version of that. I'm just taking to myself, people, sorry. So I got a question from Stephen. Is it possible to create a class like type in Julia? Yes, definitely. And usually, so I'll answer your question quickly, Stephen, it's like, definitely. So this will be section 4 for you guys, just sneaking up on it, but skip to the end. You can have struct foo x is a float 64, y is an int 64, and you can do a foo. It's not object oriented, so it's just like the data. It's the paradigm of Julia is not it's not object oriented in that way that you'd have functions with stuff. It's like a little mini program like you would in object oriented language, but you'd use multiple dispatch on your custom types. So I guess to that question before and the question before that, yeah, it's like a C struct. Yep, that's right. You have two different types, so you can have mutable and immutable. If you want to be able to change it, or if it's immutable, and they have performance implications. That's skipping ahead in the course, so I won't say too much about it. But usually this thing of like this, when you're writing code and you've made a dictionary, or you've made, and usually it's that there's a struct that you probably should have made, but you haven't worked out what should be in it yet. So usually when I'm hacking away in Julia, the progress is like, oh, I don't know what I'm going to make in my struct. Oh, I'll use a dictionary, I'll put some stuff in there, and then when it gets a little bit more solid, I'll use the name tuple, and then eventually I'll make a struct. You don't need to do it. You can go a bit type crazy and make a million structs when you're learning about this stuff. Bit of taste, and only just doing the ones you need to do, like working with the base data structures is fine most of the time. But yeah, it's interesting when you get to using multiple dispatch and you'll make a function that works on X's type foo, so you can do all that stuff. And yeah, that's where it gets cool. And making things like using your own structs in something like a differential equation solver for some weird numerical type you're going to make is the cool thing you can do with Julia, and you can extend. You can do some really cool stuff that way. I hope that answers your question, Stephen. Yeah, some problems are better off using Dicks. Like, it's just easy to work with dictionaries. They're mutable and you can change stuff. But again, if you're worried about performance, it gets slow. When you're getting something from these tree-like data structures like JSON, they'll come in as Dicks anyway. And if you're just working with them until it's easier to just have this thing and it's got some stuff in it, and get the keys and work with it. Other times you want a bit more structure because you're going to do something specific, and then it's better turning it into your own structs and working with those. Yeah, so in this problem above, I wouldn't have used a name tuple. I would have made, let's give you an example of using this thing. So struct my priority. Can't spell. And you can go age is int, occupation is a string. And one thing you can do is you can overload the functions in base, so is less, to work with my priority. And then you can go equals x dot age. So you need 2 for is less, right? I'm going to run away out of the page. So then, because this base is less, you can use this everywhere. for your type, and we're just going as the age of the person 1 less than the person 2. So if we go A equals Y. Sorry if this is confusing to everyone. And we go A less than 3. That's cool. I don't know if you know if that seems cool to you, but I think that's really awesome. You can do this overloading of the base is less, and then all these other things will happen for free downstream. Yeah, bit of a sideways thing. I hope that was useful. Yeah, if I run my Julia program, just having it going in the background make it significantly slower to run? No, that's like, I'm going to talk about this a bit later, maybe this lecture. We probably won't get to it this lecture, but I'll definitely get to it maybe on Monday next week, I think. But System Monitor is your friend. I don't know what operating systems you guys are all using, but I'm on Ubuntu. So I use top all the time. I can see what's running on my computer. I can see Zoom is thrashing my CPU. Julia's not doing anything. I don't know why Zoom's using so much of my computer's CPU. So it's got 1.5 cores. You can see how much memory it's being used. So Zoom's not using much of my memory. I don't have much memory on this computer. I've only got 16 gig. In Windows, it's probably System Monitor's your friend. Just check if it's actually running. Just look at what the CPU is doing, which processes are running. We'll talk a little bit about this later on. Shouldn't be slow to run. So. Cool. I had a question about like using a function as a keyword. It's probably for your homework. If you're going to go like foo, I think it's this by keyword, so that's in sort anyway. So in Julia, remember optional named arguments after a semicolon. These have been my little quick hints. So if you're setting up your function, you do the ones you need to put in. So V is going to be my array. And I've got optional one here. So in Julia's base sort, I can choose the algorithm. I can choose what is less is. So you can see straight away that I could sort an array, because I did that overload before to the question before from Stephen. It's this thing, you just have to overload is less and you get all this stuff for free. I can sort arrays of my priorities because I did this type. But by is a function. So identity function as default. So identity 3, oh, can't spell. Identity 3 of 3, 4 is 4. That's the default. But what by will do in sort in this implementation is map it over the array. So it's something you apply to the array before you do the sorting. So it's like this map here. So a natural thing. Natural thing to do is to do it as an anonymous function like this. You could go sort 1 to 10 by x goes to x squared. That's not going to do anything interesting. Minus x squared, maybe that's interesting. Yeah. So the trick with doing these sorts of problems, probably should we start again soon, is to make sure you're testing these little functions one step at a time. If you can try and do too much in one go. Yeah, it's just an anonymous function that you're going to pass to it. You're going to go like, oh, if I want to do something, I'll make an anonymous function and map over the array before I sort it. that's what the whole by keyword is. So like you might want to do something funky to an array of strings, like you want to get the first one, you know. I won't show you that because I run out of time. So yeah, it's a thing. So inside your function, you'll apply this function again. So you're passing a function as an argument to the function. That makes sense. Cool. All good? Cool. I'll get back to it then. Everyone's all good and back. I'll have a drink because I can't talk for this long. It's sort of sit in my room and just work on my own and don't talk to people all day. I have to come and talk for 2 hours and my head explodes a little bit. So we'll get back to it. I got another question about, can't seem to create a private post in Piazza. I don't think you can. I think they only talked about that. I think that's all public by default. Make minimum working examples. It's like, same as if you're going to go on Julia Discourse and ask a problem. It's like, if you don't understand what your function's doing, make the smallest function that has the same problem, and so other people can see it and understand it. It's like, you guys will see this when you see a big block of code, your head goes instantly. So it's hard to hard to see. So it's like, if you have a problem with like this by thing, it's like, my function's not doing this thing. I want it to split and flip things around in such and such a way. Just do the anonymous function. Just write what you've got for the anonymous function and try it on a single example. Like, you should be able to go just with one element. This is this debugging process. I'm going to go 2. I'm going to pass one thing through. 2 goes to -4 squared. That's not what I meant. I meant to do that. Okay, yeah. Make sure you sort of go from the inside out and make sure every step's working all the way through. It's my friend said it to me 8 years ago. He's a really, really good software developer, the best one I know. He said, it's just writing computer programs is having an argument with an idiot who's really pedantic. It's like they just can't tell what you mean when you want it to do a thing and it just won't do what you want it to do. And that's because they're dumb. We sort of project more intelligence onto computers than they actually have. At this low level, they're just bits and, little pushing things around in registers. They're not very clever. You build this language out and you start giving it more intelligence than it has. It's a really frustrating thing because we're people, and you talk to a person, give them instructions. They interpolate the details, whereas a computer won't do that for you at all. It's very frustrating to understand the process. So the process is just start small. I recommend using the Julia REPL. Maybe over, and my personal preference would be over using workbooks. When you're just hacking around, just go into a Julia session and hack around like this and pull your problem apart and see what's going wrong from the inside out. It's very hard to just write code and it works. I've not done it once in my life. That's, anyway, sideways diversion. Okay, so heap data structures. So really super important data structure that basically just a little bit of structure on an array, and it gives you these properties that finding the max is order 1, so it's really fast. Deleting the max, finding not the first isn't order 1. That's like looking through an array again, but always the first is just sitting there waiting for you, so it's really fast. Deleting the max is log n, insertions are log n, updating priorities log n. So you're gonna do it later on, hopefully. One implementation you can use some data structures. So data structures is a really cool part of base Julia. So you should just have it. You shouldn't have to do package add data structures. It should just be there if you do using. I'm not sure if that's true. They use it internally for optimizing things. It's so useful, some of these things, and a heap is a really useful one. And you can imagine when you're doing like a programming language itself, having a priority queue for execution of tasks is really useful. Like, what do I do next? I'm a computer. There's all this work coming up, and especially if you're doing something like you've got work coming from multiple threads, and you've got to go, oh, I'll do this thing. Having a heap there is really useful. So if we think about what we're going to do, we have a heap algorithm. Pushing it takes log n. Putting all n values in requires n log n, and then it's constant time access for the top. So total time is still n log n. So you can get, so all the time is just in constructing this array. You're going to go and put a thing in, that's one time, first element of the array, log n, log n, log n, log n. So that's way better than n squared of bubble sort. And it's asymptotically, complexity is the best possible. So, you know, if you do this theoretical analysis that I'm going to wave my hands and pretend I know how it actually works, but best possible performance for sorting is n log n. So you can imagine, so another useful thing when you're doing algorithmic thinking is thinking about, for this problem, what's the lowest possible complexity you could possibly have? So for something like an array, a lower bound on complexity is going to be log n, you know, I mean, sorry, n. You got to look at all the elements in the array if you're going to sort it at least once. And then, so somewhere between n squared is like, if you're not, you know, the probably the second dumbest thing you'd do would be log n squared. Sorry, can't talk. The second dumbest thing would be something like bubble sort where it's n squared. So the true bound should be somewhere between order n, of just like I've got to do something to every element in the array, and n squared where I do something like bubble sort. So it turns out the answer is n log n in the middle of those two. So this is an asymptotic bound. So what we'll do, and this is nice, right? Like you just, so special type of heap is this binary min heap. There's different types of heaps you'd make. So L type, I've probably shown you that one before, but just from memory, it's like it takes the elementary type of the array. So I can put an array in. So I'm giving it some type annotation here. So it's an abstract array. Doesn't matter too much. What you, again, this would work without this here, but something else would probably work too if you used it wrong. So it's not really for performance or anything. It's more for making sure the right function works on the right data type. Make a heap, initialize an empty heap, and I'm going to push each element of the array into the heap. So each time log n. And then I'm just going to go through and pop. And for the length of the array. So I'm going to go through, so log n again. Blah, 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 blah. So you get out a sorted array. It's so simple. So everything, all the magic, so again, because Julia's magical, push with a heap, it has a special, it will dispatch. And if you want to know which type, let's just go, just because it's useful. So we'll go A equals rand in 10. So H equals, so A equals first. So that's just the first element of that guy. And we want to go, if we're using push, which one's it going to be using? So this useful macro. What of them? So this is in, all right, my mouse is going to be, this is in data structures in my computer. So you can go to this line if you want to see in binary min heap and see what it's doing. Music. Yeah, so you can see the implementation in line 90. Yeah, I'll pretend that wasn't mine. Yeah, so you can see the implementation of push. So push isn't the same push you do for an array. It depends on the data type. If you want to see which one's getting used, use this at which macro. Really useful. So this is like dead simple. So all the work's in here. Everything's going on here. Okay. Maybe someone should mute their microphone. I don't know the song. I'm old though, so I don't know any songs. All the work's in push. This is a dead simple thing. And how well does it do? So we look at, again, same sort of thing. We'll do the same sort of thing. Okay, there's a bit of some bit weird stuff in here. I'll talk through that in a second. The timing, it's definitely not quadratic anymore. This scaling is looking pretty good. That's looking n log n, which is what you'd expect. It's a dead simple algorithm. As long as someone's made this binary min heap for you and given you access to this push function, you didn't have to write that yourself. This is nice, right? Like, dead simple, and it's n log n. So what's going on here? So the only weird bit in here is this, you're seeing some spikes in the runtime. And this is something to do with garbage collection kicking in. Some weird allocations and stuff. So again, this is pretty crude doing the timing this way. Use benchmark tools, use the app btime macro, do it properly if you want to do it. You can turn, Julia has garbage collection, so lower level languages, I shouldn't say low-level languages. If you say low-level languages to someone who's serious software developer, I think you mean assembly. I'm fluffy mathematician, it's like anything like C or C++ is low language to me. You have to worry about memory. So one nice thing about Julia is it has a garbage collector, and it will go through, and if you're making a mess and you're allocating things and never using them again, and you're never going to use them again, it will come through and get rid of them for you. But that's slow, and it makes timing things not as good. So this heap sort is scaling pretty well. It's way better than bubble sort. It's nice. So if we compare it to built-in sort, it's like half the speed, which, it's twice the speed, sorry. Built-in sorts, twice as fast. But if we do the same thing, you can go through this yourself. You can see this nice plot where it's, it's not like bubble sort where it's going, woof, blowing up quadratically. This thing's still growing n log n, just like this guy. If you wanted to go through, you could plot this on a log plot, prove to yourself that it is n log n. Go through the derivation of heap, making a heap and doing all these operations, and algorithmically prove that it's n log n as well. But the coefficient is different. So this is things, so you can do this asymptotic complexity analysis. And it doesn't tell you a thing about what's the coefficient at the front is. So like you can have, depending on what you're doing, you can have more expensive operations. If you're doing more memory allocation stuff, that will start to be a problem too, especially as memory gets large. That will start to bite. But asymptotic complexity analysis isn't the whole story. So you can do better, even with within the same complexity class, which is why there's this zoo of sorting algorithms, and some tend to get used and some don't. You wouldn't really use heap sort, but you'd use heap for a priority queue, definitely. Is that clear? So I guess what I want to communicate is that heap is a really, really useful data structure. You can implement this with a canny data structure, this thing called a heap, where you really quickly know what the next thing to get off popping the next thing off the list is really fast. But takeaway story is asymptotic complexity analysis is not the whole story. There's even, if you go deep into the dark depths of computer science as an academic discipline, you get these things called galactic algorithms, where the coefficient at the front is so big that you've just never actually used that algorithm in practice. And it even happens with, I think the famous example is matrix multiplication. So again, if you use your algorithmic brain, you're going to multiply two matrices together, run, dive. If you're thinking of doing matrix multiplication, like that algorithm, you should be able to work out what the complexity is. Like there's an n cubed thing you could be doing. N squared is just looking at every element in the matrix. Square matrix, so say it's n squared. One side length is n. So the complexity of multiplying square matrices is somewhere between n squared and n to the 3. The lower bound, like it's an open question, if you want to go and get famous as a mathematician, you could work out what's the best possible algorithm for matrix multiplication, because there's no proof of what the best one is, just a lower bound. And the one that has the lowest asymptotic complexity is not used. The one, like the second one, is used because it's more integrated with computer hardware in these in the way compilers work and stuff. So sideways thing. So asymptotic complexity analysis isn't the whole story. You got to worry about this coefficient too. So even though these two things are both n log n, you got to do some testing. You got to think about details of the architecture and stuff of the computer will start to matter. So what is the built-in sort? And this isn't actually a simple question to answer because Julia does multiple dispatch, like I sort of intimated out a few times. Depending on what your array is, it might do some different things. But most of the time it will use Quicksort. And so, but famous one in this one is merge sort. So this one has a really old history in computer science because, you know, in the first lecture I was talking about the von Neumann architecture. Merge sort, I think, was first suggested by von Neumann. So he's in the 40s. So this is like World War II sort of time frame, was when they were starting to worry about algorithmic complexity of things. And I'm pretty sure it was him and another guy who came up with merge sort as the first published implementation of merge sort. So again, you're using your algorithmic brain. You got to break the problem up. Bubble sort's not, so heaps one way, you can use a canny data structure. The other one is like, can you break the problem up into subproblems and solve those and then put the results together? So you don't want to be doing this bubble sort thing, sweeping through, sweeping through, sweeping through. It's a complete waste of time. So merge sort is, I think, you guys have all got it in your homework to do Quicksort, so you're probably already all over this and you'll be able to explain it to me. So what it's, again, we were talking about before, it's completely fine in Julia to define a program that calls itself. So the idea of merge sort, I got this little GIF because it explains it really well in pictures. So this is just off Wikipedia. The whole idea is you subdivide the array into the smallest, or wait for it to roll back around to the start. You start off with an array, and what you're going to do is subdivide it and subdivide it and subdivide it, sort those, and then merge the sorted results. So that way you're going to do far less comparisons than you would in bubble sort. So bubble sort is going to be n squared. We're going to get the number of comparisons down to n log n. So we start with this array 1 to 8. Let's finally flip back around to the start. So start with this array, it's all out of order. Kind of break it in half, break it in half again, break it in half again, break it in half again, break it in half again. All these subproblems. And then we're going to keep track of 2 indices. And if this one's bigger than this one, we put it that way. Then we get the first one of this new array, or the subarray, sorry, and then put them in order. So this is the name of merge sort, is like you take the low bits and then you start merging break it into all these subarrays down to the lowest level, and you merge them as you put them back together. So you just got these pairwise comparisons. And you got to keep track of which one's the biggest, which one's the smallest. So then it goes over to this guy, blah, blah, blah. So you can see the picture of what's going on there. It's sort of better than reading code. So what this will do is we've got a div here. So you've got your data. N is the length of the data. We're going to do this. So if you're not sure, div is integer division quotient. So it computes this truncated to an integer. So, you know, you got to make a decision about where halfway is for odd numbers. It's not that important. You just got to do a thing. That's what this one is. So then you're going to break the data into 2 bits. So up to half on the first iteration of this, the first steps of this recursion, you'll go to halfway. And you go from halfway to the top. Julia indexing, you're going to do a +1. Starts at 1. So if you're in Python, you go to p-1 and then p to end or to end. So you're going to call this merge sort, basically do this animation, and then you've got these top and bottom indices. And then as you put them back together, you combine the arrays, and then it comes out sorted. So this isn't, I guess this is a challenge for the reader, or you guys, is go through this and make it fast. So problem with this one is it's allocating all over the place. So things I was saying before, like if you're thinking about, cutting this array, do you need to do this? Do you need to make new arrays called data top, data bottom? Can't you keep track of, just keep track of some indices or something if you wanted to make it fast rather than allocating a whole new array? There's a minimum amount of allocations you have to do, but this one's just sort of being, just being lazy and just allocating way more than it should. So it's probably a good one. I'd say this is a really good example if you've got free time to go through. Make sure you understand this algorithm. Make sure you understand why it's n log n. I suppose we can do that. Then you don't have to worry. We can talk about that here. But I think there were some questions about, like, how do you prove runtime of algorithms? So there's a nice result. We'll get to that, but there's a nice result from computer science about particular types of recurrence relations and proving what their runtime will be. Sort of like just a plug-in from a table. You can just go, oh yeah, if this bit's this big and this bit's this big, plug it into this thing and get the answer. Yeah, so hopefully you can see that. So it's a divide and conquer algorithm. All of these, Quicksort is a divide and conquer algorithm too. So you're basically just breaking it up into little bits, and then you merge the results and keep track of how you merge them, and you merge them in a way such that it comes out sorted. Each subarray as you're coming back out of the recursion will be sorted, and then it comes out sorted. So again, this one's, as I said, this one's pretty lazy with allocations and stuff. It's not like a super duper tight implementation. But again, that's software engineering tricks where you're going to try and reduce number of allocations. Don't allocate new things if you don't need to. Just reuse things and keep track of indices. But it's harder to write, so this is good to just quickly make it work. So if we're comparing it to built-in sort, it's not winning. But this guy in timing, this is a hint for you guys that something's off, is time will also report number of allocations. So this is doing 3 million allocations of, and that total of that is 0.5 gigabyte. And so 21% of the time it's spending in garbage collection, just as a bit of an interpretation for using the time macro to get a bit of a hint about what might be going wrong with your algorithm. So if you're allocating, the built-in one does 2 allocations. It's tiny. But they're big allocations each time, but it's only doing 2 of them. So if you're allocating heaps of times, it's not great. You can be doing a lot better. Okay, so this is, I'm just gonna, so you've got this recurrence relation where you're doing stuff where you're cutting it in half, and there's some order n to this. If you go through this algorithm as a recurrence relation, you think about at each recursion level, what's it doing? It's doing something that depends on cutting the list in half, and then it's doing some stuff of order n. There's a nice result called the master theorem, which isn't actually very old. It's surprised how not old this is. This is from the 80s, I think. Yeah, 1980. It's probably well known in mathematics for a lot longer. Often these things are, but someone finally decided to publish it. Not all recurrence relations can be solved with this thing, but it's basically, if it's of this form, you've got these coefficients a, b, and a function of order to n, of order n, then you can find out where you are and plug it in and it will give you the order. So there's a little bit of a demonstration here of this. So that's a way of doing a proof. You can use this known result of the master theorem, pointed that from, yeah. If I see which form of problem I have, plug it into master theorem, it'll go, oh yeah, comes out n log n. Yeah, that's really bright, really rushed and quick, and I don't want to go too fast. I don't want to go too much detail. You guys can look at that stuff. Go and look at the original paper. It's not a thing I ever got told in undergrad, but you can go, if you want to understand something, usually the person who came up with it understood it the best. Often they were way too smart and they're really confusing people, so it's hard to read, but some of them are actually really lucid, and it's actually easier to read the original paper to understand what's going on. But you can see how this would be useful. Like, you got a recurrence rule. If you're doing a divide and conquer type algorithm, you're going to end up with this sort of recurrence relation. The coefficients out the front will be different depending on what you actually do in your algorithm. Plug it in, see what you get. Very useful result. Merge sort, that was it. Any questions? I guess, yeah, if you guys are on the homework, you probably already implemented Quicksort yourself, so I don't know how much I need to say. It's, you know, it's all over the internet. Finding implementations. We'll talk about that though later. So Quicksort is another variant of a divide and conquer algorithm. So we're not going to do an implementation, but pseudocode from Wikipedia. So two functions where you partition it and you keep track of these high and low indices. We start on the outside. I don't know if I want to say too much because it's like you guys will understand it by implementing it, and talking about something is usually not the best way to learn. It's usually trying to do it yourself, especially with these sorts of things. You've got this non-negotiable amount of suffering you have to do before you understand things. Yeah, some videos. So an interesting point though is Quicksort's worst case complexity is n squared. So you can imagine all these different types of arrays that come into your function. The worst possible case is n squared. On average though, it's n log n. And it's sort of like, this thing of like, I'll try and say it a few times for you guys, but the asymptotic analysis is not the whole story. Sometimes these worst cases are pathological. Average case is good to know, but you know, it's the distribution of your data is really important. Like, so for example, like your array is almost always nearly sorted at the start, definitely changes how you would approach these problems. And remember I was saying early on with bubble sort, you've always got this option of an early bail in bubble sort. You can just sweep through and go like, do I not need to do anything anymore? And I can stop. So having these early bails are important. Yeah. And again, do it in place if you can, because you don't have to allocate memory. Algorithms, that's it. So what do I think is important? So if I'm going to do a summary, like, I guess I've seen a few questions about some of the assignment stuff and what's important. You know, how do you make something fast? How do you tell what's making it slow? It's really just counting, you know, it's not. So if you have a recurrence thing, it's not so straightforward. But with things like bubble sort, you got to go and look at what your particular function is doing. So this is all the way back at the top. So it's going to take a while. Yeah, it's way further back than I thought it was. You just got to look at these rate limiting steps. You know, this thing, it might be an extensive function. Well, there's a hint for you guys about passing a function. There's asking the by keyword. There's an example of passing a comparison function, but just you've got rate limiting step in here, and you're doing this thing twice. So think through your particular problem and see if, you know, what's the expensive step you're doing? Is there a better way you could be doing it? Can you exploit the structure of the data you've already have? Big one is making sure you don't do things twice or more than once. Like if you can just do something once, only do it once. Often, you know, turning the problem inside out, you know, if your searching is bad, if ever you have a problem where you have to search through something to find the solution, it's kind of bad. And maybe you don't need to be searching. Maybe flipping the problem around means you can do it a different way. It's actually hard though, because like there's no, it's one of these things like algorithms is not like there's one thing you always do and it always works. It is problem to problem, and it's a bit of a mental game. So, but you're all maths grads, so you know you're all smart. You think about how you might turn the problem around. And it's basically just always just counting. Complexity analysis is just counting. You do things less. If you can do things less, they'll be faster, asymptotically. But like the heap sort, details of implementation and whether you're allocating memory or not will make things slower. So you do have to worry about that, but that's usually the second problem. All right, cool. I think that's it. I think that's all I wanted to say on this stuff. Does anyone have any questions before we move on to the next bit? No, I'll take it as we're good. Everyone's happy. No questions. I'm sure you're all like that stuff. Cool. Now what? Okay. So now this is going to be fun because this will be more like useful software, everyday software engineering stuff, not, you know, algorithms are fun to think about, but in your day-to-day life as a software developer, you usually, you know, the usual software developer is not re-implementing algorithms, they're reusing algorithms. So when you're coming to a new problem, you use what's available. So don't go off and reinvent the wheel. You should use what you've got available to you. It's like, if you don't have to be smart, you know, if you can use other people's brains, it's not like university where you're getting tested. It's like, if you can reuse other people's work and you know it's good and you understand how it works, you know, don't be scared to use it. We're going to talk about tooling though. So this is more like professional practice stuff, which is really weird to be teaching in a maths undergrad, more like an engineering course. So tooling, we're going to talk about three things. See how long I spend going through this stuff. Hopefully not too quickly. Some of you will be really familiar with this stuff. I don't know that course, but I assume, yeah. Some of you will be really familiar with this stuff. So I just quick poll of like, how many people have used Unix command line? Like, you probably use Windows command line and stuff. Okay, we've got a lot of haven't, yes, no. My rough things like oh no, it's lots of no's. Okay, cool. So I can teach you stuff there. That's cool. It's kind of easy. It's just a lot of stuff to remember. So Unix, we're going to talk about Git and GitHub. So they're super useful. So when you go and try and get a job in software and you don't know about version control, you are in trouble. The learning curve for Git is, Git's not a friendly tool. I admit that. It's easy to use naively though. There's a problem when you read stuff about software engineering. It's like everyone gets excited about what, say, Google does. You know, these large software organizations. The way you use it as you're a beginning programmer, it's like, it's not the same. You know, you can be quite naive and do simple things, and complicated stuff, you can push it off till later. You don't get familiar with stuff, just, you know, go in the kiddie pool before you break things. Git and Unix command line can be quite unforgiving if you do the wrong thing. It's like, but it used to be worse. It's not the same as it is now. Git, I know many developers who are very, very experienced and very good developers who have trouble with Git sometimes, so don't feel bad. But the problem with using Git is when you're using it with lots of people. It's like, if you're just using it on your own, it's actually pretty straightforward. We'll talk a little bit about using IDEs, so an integrated development environment, and we're recommending Visual Studio Code. I use VS Code now. I never used to. For the longest time, I did not use an IDE at all. I just use basic tools because it's fine. But we'll talk about that when we get to it. Cool. Okay, so I guess the next poll is like, what OS is everybody on? Like, just as a rough thing in the Windows. Oh, we've got an Ubuntu. Lots of Windows. Mac, cool. Mac. Windows. So it's getting, so yeah, cool. We've got a broad range. I myself, I'm on Ubuntu. So most software developers will use Mac and Ubuntu because it's easier. It's an easier development environment. Depending on the type of work you're doing, if you're doing .NET applications, so like you're using all the Microsoft infrastructure, you know, it's easier to stay in Windows. But if you're doing server-side stuff, so computers running on the internet, serve web pages, they all use Linux basically these days. They have for a while. Why is a interesting question. So it's like you're gonna be careful asking that question on the internet. It used to be worse. People are snobbish and idiots really. It's as a software developer, it's easier if you have more access to low-level things, but at the same time, if you have access to low-level things, you can shoot yourself in the foot. So, you know, be a little bit careful. It's better than it used to be though. Like things like Ubuntu, if you want to experience using Linux after doing this stuff, I recommend, I'll just put it in the chat because I'll get it wrong. You probably all have, if you're all on Windows 10, you'll have Windows Subsystem for Linux, I think it's called. Has anyone seen that or familiar with that? Oh, I sent you a direct message. Sorry, everyone. Whoopsie. Windows Subsystem for Linux. You can also use hypervisor. Two things you can have a look at if you want to have a play with your computer and you're on Windows. Anyway, have a look up Windows Subsystem for Linux or on hypervisor. You can run a VM with Ubuntu on Windows. If you want to start having a bit of a play with operating systems and use more like a Unix environment. If you're on Mac, you're fine. So one of you guys was on Ubuntu, that's cool. Things to have a look at, but you can just use Git Bash, I think was recommended. I'm not very familiar with that. Windows command line doesn't support all the things you might want to do. What are we talking about? So operating systems. Again, computers are a disgusting pile of abstractions. So again, that's like I've said before, I don't know what's going on in the CPU. I don't know what's going on at the OS level. It's a lot. Someone asked about having Julia running in the background. It actually depends on your OS and what your OS is doing. Your OS has this ability to run multiple processes simultaneously, and depending on which type of operating system you're doing, how good it is at doing that, that's the answer to your question. Like, it shouldn't matter, and these days it usually doesn't matter. But the operating system, what have we got? I didn't actually see what. Yeah, that's not what it would be. So it's basically, it's doing all the low-level stuff. So it's the thing that's talking to the CPUs. It's the thing that's talking to the hard drives. It's taking all the user input and all the devices. And doing all the networking. So it has its own programs for interfacing and managing the system, graphical user interface for files, and importantly for us, the shell. So it's called a shell, I think because it's outside. It's like a thing that's around the kernel. So the operating system, so Linux has a Linux kernel. When you say Linux, it's like Linux is the bit, it's just the OS, so it's doing all this process switching and stuff. And you have a shell around it that's basically, you can think of it like the Julia REPL. So I was thinking about how to do this part of the course, and I've like got all this work stuff in my environment variables, so I could have a disaster where I put like a secret password on the internet and get fired straight away. So I'll be a little bit careful. But here in Linux, the default one that comes with nearly every version of Ubuntu, every Linux distribution that you could get, it's called Bash. And this thing is a thing that has an API to the kernel. So you do some stuff and it will do stuff for you. So I guess the most, yeah, so that's this thing Bash. So I'm here, I can call Julia, blah, blah, blah. You've seen me do this. This is what I'm doing. I'm in a program that's called Bash that talks to the kernel. So you can actually have different ones. So it's not like this is just, you can make a program that has its own shell. That's fine. There's lots of different, like if you're on the Linux side of things, there's like lots of people use different types of shells, things. They don't necessarily use Bash. I have a friend who uses one, a strange one that does nice highlighting and stuff. I'm pretty lazy and I just use whatever's there. So this shell scripting comes from the days when, you know, they're really old. Before computers even had graphical displays. So, you know, it's really old school, blah, 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 using it at this low level. Don't be scared though, it's actually easy and there's not much that can go wrong. In the old days, you used to be able to like delete your own hard drive if you did the wrong command. And some people, when they were teaching you when you're a beginner, they'd go, oh yeah, do this. Hey, I deleted my whole hard drive. Yay, thank you. Now there's protections around that stuff and they won't let you do it. But basically, yeah. So, you know, all this stuff is just, you know, window dressing around this low level talking to this kernel. So Unix is a classic operating system. So Unix is ancient. It's from Bell Labs. So has anyone heard of Bell Labs? AT&T Bell Labs? Is that a thing you guys are familiar about? No, AT&T. It's back in the 70s. It was they were huge and they had like Nobel Prize winners working there and they did amazing things and they were just like this, like sort of like Google are today, where it's like one of these big companies that have heavy research department and very, very smart people working there. And a lot of the things that make up the modern world were invented there. So like it has links, you know, this is where all the back to the beginning, like invention of the transistor coming through. It's like one of these places was Bell Labs. So I think Claude Shannon was one of the first ones. Is that someone you guys? Pretty sure he worked at AT&T Labs. He basically invented information theory. So Shannon entropy is a thing you can look up about. You know, it's useful information. But all the way back through, all these things like Unix and C programming language, they all came out of this place, and there's all these people, amazing, very, very bright people coming up with them. So there was a very, Unix was a joke. I think the name was about, there was this multiplexed operating system. So you could run lots of different people running on the same computer. They went off and made a small version of it that's called Unix. And it was meant to be that you could only run one thing at a time, I think was why it's Unix. But now, of course, you can run multiple processes at once. Mac OS is based, there's like a, I'll see if I can find the family tree. Oh yeah, this is here. So back in 1969, there's the first version of Unix. And it was all, you know, AT&T research stuff. And then it's split off into all these different things. So over here, so if you're in Linux, that's like me. So using Ubuntu or Mint or whatever, Red Hat, whatever, all these different distributions, they're all using Linux as a kernel. They were inspired by Unix, so they're a bit of off the side. Minix is actually in every Intel computer, I think I read recently. That's kind of bizarre. Comes with a little distribution of Unix inside it. I don't know what Intel have it there for, but that's interesting. Mac OS actually comes from a version of Unix from the 80s. So Steve Jobs and that, when they were doing Next Step, doing all this crazy stuff, they went to That's where Mac OS comes from. So that's actually got a straight line to the original Unix operating system. All these other ones that you might have heard of, like Solaris and there's HP, OpenBSD, they're all Unix things that are still hanging around. So Windows is not Unix based. So these tools, this Unix command line is a super useful thing. Windows has things that impersonate it, but you can have a VM now. And Windows is supporting more Unix tools. So there's these things, Windows Subsystem for Linux, and you can use hypervisor to start a VM in most Windows 10 distributions, I think now. So again, the shell or command line interface lets you do simple and complicated tasks by the command line. There's lots of videos linked here. Okay, you're not required to build up a command line knowledge as part of this course. I recommend using Git Bash. I'm not familiar with Git Bash, but I imagine there used to be lots of, like, Cygwin was one years ago that used to give you this functionality. And it's really, really useful. So lots of the things you can do under Unix, Unix style is really useful. And Mac, you can open a terminal. On Linux, you just open the terminal too. That's this black screen I keep clicking on off the side. Okay, now, as I said, like, you can make your own shell. Julia has a shell inside of it too. Has anyone seen this? It's like, if you start a Julia session in your REPL, you can press semicolon. Cool. So Emma has. Yeah, cool. So, oh, you only showed you. All right, awesome. So you can do most of the things you can do. So you can go ls is thing. I'll say a bit more about this, but you can do things. They are actually different though. I had an example. I thought, yeah. So I'll say a little bit later about these commands, but this is just a hint that these are programs. So like your bash, your shell script will do different things. So this is a useful thing that bash can do that the Julia shell can't do. So what I've defined here is I want to go for all these elements in P, C, D, B in with A. So like you can imagine, you know, this is the thing you're allowed to do in bash. If I try and do the same thing in the Julia shell, let's see what happens. No, it doesn't know what the hell I'm talking about. So they're not all the same thing. They're actually just programs, and they're an API that's like the REPL talking to, you know, the low-level stuff. So things that are supported in one are not necessarily supported in the other. So, you know, they are different, and different things will work in one and not in the other. And you'll have access to things that you might not have in one that you will in the other. So they're implementations of it. Hope that's clear. That's just a thing to keep in mind. They're not all the same. And you can change them and use a new one. Okay, so I guess a big part, you're all familiar with this, I'd say, just being a computer user is just a file system. So let's go. Let's see what's on my computer. Try not to show anything secret. This idea that, you know, there's some low-level thing and there's a tree for navigating through all the things. What do I want to show you guys? So there's some stuff, you know, you can navigate around, you know, you can do it graphically, it's fine. That's fine. So you've got access to all the same things in the shell. So probably the first useful comment, first useful thing is ls. ls is a function that you can call with bash. So we've given a list. I'll probably go through them all slowly, but just to give you an idea. So it lists all the things in the current directory. If you want to know which directory you're in. So we go, I'll just make sure I'm not jumping ahead. Yeah, so you've got one to keep in mind is these slashes. So yeah, so these slashes will be different depending on your OS. So I think I've said this to someone, but I should show it to all of you. It's actually a problem if you're for portability. So when you're writing computer programs, you want things to work on different computers, and the slashes will drive you crazy, and spaces will drive you crazy too. I think in one of the consultation sessions, we had a weird problem with Anaconda and spaces in the username thing. So one of the things you start getting a twitch when people put spaces in file paths, like use underscores. You have less problems. My point was, you want to be aware of let's go. I'll just get some random stuff off my computer. Join path is a really useful function because it will give you the right escape. It'll give you the right things for your file separators. Join path, absolute path on Windows is a drive specification, doesn't have to drive computer to join the preceding paths. So if you have something like this, it will give you the right slashes for your OS. And if you try and use the same thing on a different operating system and the file, you know, the place to where your file is the same, use join path, it'll make your life easier. In Bash though, ls, you can see what's in the directory you're in. So this is my home directory. I've got a bunch of work stuff that I shouldn't be showing. It's a tree structure. This directory structure is always a tree, same as like this heap. You know, we have a tree there as well. You can go down with CD. So change directory, I think it's supposed to stand for. Yeah, let's go. Where do we go? Okay, so I went change directory slash. So slash is the lowest level, and I went into this one called bin. And this guy is interesting because if I ls in here, you can actually see ls. That's where this guy lives. You should also see, oh, there's lots of stuff. You should also see CD. So these things are little programs that live in here. Anyway, so you can go down to the bottom with the slash, and you can go, yeah, you can see permission levels based on color as well. That's cool. Let's just go somewhere else. Let's see what's in here and copy. So more stuff, blah, blah, blah. So that's going up. So CD change directory going up, CD ... to go down. So if you want to navigate around, so CD ... to go down. To CD just takes you back to where your home. It's like go teleport back to home. Another really useful one is PWT. So home Paul Bullet. Basically, so they were those ones. So ls to show what's there, CD to change directory, PWD to print working directory. It's really, this file system organization is like a human level thing. It's like, it's a really useful way to organize. You get really used to navigating around like this. Really useful thing I'll say as well is to tab. So start typing something, AWS, won't go in there. But you start pressing something and you press tab and it will do text completion, which is really useful and save spelling mistakes and stuff like that. Okay, well, let's, oh, someone has to run. Okay, no worries. That's the basics of file navigation in here. That's the really easy one. So you can also, we'll do just a little bit more of some simple ones. We can make a directory, make the test lecture. ILS. You see this guy test lectures here now. I can CD into test lecture, and there's nothing in there. It's a new thing. So I go back down. So I've made this thing. I want to get rid of it. Render test lecture. He's gone. This is this thing about being careful, because like you remove this stuff, it's just really easy. The design of all this stuff is, the way to think about it is that it was all for when graphical displays weren't even a thing, and it's really useful. But the thing is that this is a super useful way of driving your computer. You can automate this stuff. You can write scripts that do all this stuff for you, and you can do it repeatedly. So like when you're writing computer programs, a lot of this stuff is really, really mechanical, and you can write scripts. They're called a bash script, usually .sh extension in Unix, and you can write this list of things you're going to do, and you can run them and run them and run them, and it's really easy to automate things. And so you can set up a directory structure, call Julia, do a thing, go back in. I'd also say though that like the more modern stuff is like whenever I'm at this low level stuff, I nearly always just jump into my programming language and start doing stuff. So if you're in Julia, you know, you have these things like read. So I can do all this stuff that I was just doing. I can iterate through. So like even without going into the shell, like I can do ls as well. I don't have to do ls is like read. I can open files, I can make files, I can delete files, all from within Julia. So, you know, I guess a more modern thing is like the first thing you do when you start up, like every computer with Linux will have bash. You can use bash, download the thing you're going to run, and then run that straight away. So people do that in Python all the time. So just started on this stuff, showed you some basic stuff. You'll find on the internet like a million cheat sheets for this stuff. That's just file navigation, so just moving around. I'll go when we go tomorrow, I'll go through a bit more of this stuff. If it's, you know, if you're really all over this stuff, you probably find it a little bit boring, but please come with questions if you've got them. Yeah, I guess that's where we'll stop. So we've just started, you know, this is how you'd navigate the file system in Bash. You can do the same thing in Julia. It lets you run all your programs. I'll go through some things I think are useful, and hopefully that's useful for you guys. Any questions on what we've done so far? Sorry, just go it once. Yeah, sorry. So if that wasn't clear, every time you start a terminal, you'll have this, you'll go into bash, like in Unix and in Linux, you're going to bash, and bash gives you access to all these things. I think the point I was trying to make is that the most useful thing you'll probably do most of these days is to start your programming language. You know, you'll do Julia and call your function. And you can do all this directory navigation stuff from within most of these programming languages these days. So it's like nearly like the new version of Bash is these high level languages. Like people do it in Python, they'll just do all the file manipulation stuff from within a Python script rather than doing a Bash script, set stuff up and then go into Python and do the work. I think that was my point. I hope that's clear. So Windows questions, I'll defer to anyone else because I haven't used Windows in over a decade. I get a bit terrified when I have to do it. I would honestly, we'll talk about this later, but I would just use, if you want to do terminal stuff, get VS Code. You can run a terminal in VS Code. I'd just use this. This has got all the same stuff. You can do it from there. This will have, I don't know if this has all the, if it's the same as Bash, but it'll have all the stuff. That's the easiest one. So we'll talk about this maybe next time. We'll get into IDEs and all the useful things they can do. Any other questions, guys? thank you for your patience. It's really late, these lectures, so appreciate you all coming. My family have been tormenting me because they've all eaten nachos without me, so I'll go off and eat now.
Hey, Paul.
Oh, yeah?
Oh, hi. I have an assignment question that I'm a little confused about.
Okay.
Is it okay if I ask it now or a bit later?
Yeah, that's fine.
Oh, awesome.
We'll probably just want to cut it out for the recording, but I'll just let you know. Yeah.
Yeah. Okay, cool. So I was working on question 8A, so where you have to write your own determinant function.
Okay.
Using the first row of the matrix, right?
Yeah. Just make sure I understand. Okay. Yep.
Yep. So I kind of like looked at the matrix to see if there's like any, like the matrix for 3x3 and the matrix for 4x4, and tried to see if there's like any like patterns or anything.
Yeah.
Because I'm really confused on where to start for this question. Because I can't really see any patterns for the matrices as they get big, as n gets bigger.
It's that thing of, man, linear algebra a long time ago. If you look up how determinants defined, it's this, there's a recursive. So like if you start with a 2x2 matrix, you've got this D minus BC, right?
Yeah.
Then you can go pick any of these things and you can go, oh, A is this submatrix. It's this thing times the determinant of this thing.
Yeah.
This thing times the determinant of this thing, this thing times the determinant of this thing. This pattern goes all the way out for n. So
yeah.
You just go, I'm going to do determinant of the submatrix off the side. So iterate through, cut out this bit, do the determinant of that until it gets to a 2x2 matrix where I know what the answer is.
Okay.
Does that make sense?
So basically we're finding the determinant of submatrices until we get to 2x2.
Yeah, because you know what that determinant is, and this pattern of going, oh, it's this coefficient times, so this is 3x3. This pattern for 3x3 where you're going to go like A times the determinant of this matrix minus B times the determinant of DGFI, C times the determinant of DEGH. So that's the determinant again.
Yeah.
So you can make the 3x3 one in terms of a bunch of 2x2 ones and some multiplications and sums.
Yeah, which you can do for the 4x4 one as well, just a lot.
Yeah, so it's this Laplace expansion. So you'd be doing this recursive thing when you're calling it again and again and again with submatrices until you get it. Does that make sense?
Yeah, it does.
Okay.
So yeah, I'd look more into Laplace expansions for this question.
Hope that helps.
Yeah.
Cool. Okay. General pointers on how to cut down the number of runs of check Goldbach. I've got it running 26. It takes about a minute. Down to see 21 once. Still running a lot. Okay, that's a hard one. I can't give too many hints with the Goldbach one. That's a good question. So that's I'm trying to give you guys hints when I'm talking through the lecture of like, think about what's slow. And if you're searching, it's slow. Maybe there's a way where you don't need to search. Or you can make searching fast. You know, like I talked about, like, you know, if you've got a sorted array, it's quicker to do searching on a sorted array than it is on an unsorted array. If you don't give it a hint that, you know, yeah, there's lots there. So yeah, there's lots you can do. It's interesting. So yeah, as I was saying before, Andy got it down to under a second. I got it to about a second and a half. We did the same. This is the thing, because there's like, we did the same algorithmic tricks, but he knows more about Julia than I do. He's quite smart. So yeah, so you can get really fast. You've got to think about how to reduce the number of computations you're doing at every step. It's a bit of a game. I won't give it away because it's kind of fun. That's all I'll say. Okay, thanks guys. If there's nothing more, I'll jump off. It's all right. Good night, guys. See you tomorrow.